Hi everyone, I'm Flávia Secato. I'm from Free Astroscience. This is not AI voice, it's my real voice. Astronomy gives us access to the deepest layers of reality. Through it, we study time, matter, energy, and the physical laws that shape everything from atoms to galaxies. Every telescope acts as a time machine. The light we observe tonight left its source millions or even billions of years ago, carrying information about the history of the universe. By analyzing that light, we reconstruct how stars are born, how galaxies evolve, and how the elements that form planets and life came into existence. This presentation explores how those discoveries reshape our understanding of life and of your own place in the cosmos. Earth biology and human awareness are part of a much older physical process that began long before our planet existed. Seen from this perspective, the universe becomes a vast laboratory in which reality itself is constantly being tested, transformed, and organized. And it's within this ongoing experiment that our existence takes shape. When we study the universe, we are not only studying distant galaxies and stars, we are studying our own physical origin. Modern cosmology shows that the universe began approximately 13.8 billion years ago, a value measured from observations of the cosmic microwave background radiation by missions such as WMAP and Planck. The Earth formed about 4.54 billion years ago, based on radiometric dating of meteorites and the lunar rocks using uranium lead isotopes. These samples represent the oldest solid material in our solar system and gives us a highly reliable timeline for planetary formation. In contrast, anatomically, modern humans have existed for roughly 200,000 years, as shown by fossil evidence and genetic mutation rates. This means that human history occupies less than 0.005% of Earth's age, highlighting how recent our appearance is in cosmic terms. However, what makes humanity truly remarkable is not the brevity of our history, but the nature of our material composition. All elements heavier than hydrogen and helium were produced inside stars through stellar nucleosynthesis. Using spectroscopy, astronomers can identify the chemical composition of stars by analyzing the absorption and emission lines in their light. These same elemental signatures, carbon, oxygen, calcium, iron, are found in the human body and in Earth's crust. Low-mass stars create elements up to carbon and oxygen, while massive stars produce heavier elements through fusion up to iron. The most extreme elements, including gold, uranium, and many rare metals, are formed during supernova explosions and neutron star mergers, where temperatures and pressures become high enough to create the heaviest nuclei. Observations of supernova remnants, such as the Crab Nebula and Cassiopeia A, reveal expanding clouds rich in these heavy elements. These materials mix into the interstellar medium and later collapse into new star systems. Meteorites preserve isotopic signatures that match this stellar debris, confirming that our solar system formed from recycled stardust. This means that every atom in our bodies has passed through at least one star before becoming part of us. We are not separate from the cosmos. We are the product of billions of years of cosmic evolution. Life on Earth is the result of nuclear physics, gravity, and chemistry operating on a universal scale. This timeline compresses the entire history of the universe into a single day. Midnight marks the Big Bang, when space, time, energy, and matter came into existence. A few hours later, the first star ignited, beginning the process that will eventually produce all chemical elements, heavier than hydrogen and helium. By 2 in the afternoon on this cosmic clock, our solar system forms. The sun and the planets take shape from material recycled from earlier generations of stars. Earth appears as part of this process. Life begins late in the day, around 9:30 in the evening, when the first simple organisms emerge in Earth's oceans. For most of the cosmic day, the universe exists without biology, and for most of Earth's history, life remains microscopic. Humans appear at 11:59 and 58 seconds. All of record history, agriculture, science, art, technology, civilizations, fits into the final 2 seconds of this cosmic day. This perspective changes how we evaluate time, importance, and permanence. Our species is extremely recent, yet it carries inside it the entire evolutionary and cosmic history that made it possible. Every thought, every culture, and every scientific discovery emerged from a process that began almost 14 billion years ago. When we think about time in everyday life, we imagine something simple and steady, a clock ticking forward 1 second after another, tick tick. In physics, time is something far more subtle. It is not a fixed background against which events unfold. It's a dynamic part of the universe itself. This understanding begins with Einstein's revolution. Before Einstein, time was assumed to be the same everywhere. His theory of relativity showed that this is not true. Time depends on motion and gravity. The faster you move through space, the slower you move through time. The stronger the gravitational field, the more time slows down. This is not theory alone, it has been measured. Atomic clocks placed on airplanes and satellites runs slightly faster than identical clocks on Earth. Astronauts aboard the International Space Station age a tiny bit more slowly than people on the ground because they are moving quickly and experiencing weaker gravity. Modern GPS systems must correct for this effect every day in order to give accurate positions. Time is therefore not universal, it's flexible and shaped by the physical conditions of the universe. That flexibility becomes extreme near black holes, which represent the edge of time itself. A black hole forms when a massive star collapses under its own gravity, compressing matter into an extraordinarily dense region. Near its event horizon, gravity becomes so strong that space-time is deeply distorted. According to relativity, time slows dramatically in such conditions. To a distant observer, someone falling toward a black hole would appear to move more and more slowly, never quite crossing the event horizon. Their image would fade and freeze, stretched by gravity. For the falling observer, however, time continues normally. They cross the horizon without noticing anything special at that exact moment. This shows that time is not something everyone experiences in the same way. It depends on where you are and how you move through space-time. The universe also allows us to look back in time. When astronomers observe distant galaxies, they are not seeing them as they are now. They are seeing them as they were when their light left them. Light takes time to travel, even at its enormous speed. The James Webb Space Telescope detects infrared light that has traveled for more than 13 billion years. Some of the galaxies it observes formed shortly after the universe itself was born. This means astronomy is a form of time travel. Each image is a record of the past. The deeper we look into space, the further back in time we go. Telescopes therefore function as instruments of cosmic history, revealing how stars, galaxies, and structure evolved. Astrobiology is the scientific study of life in the universe. It brings together biology, chemistry, geology, and astronomy to answer one of many oldest questions. Is life unique to Earth, or it's a natural outcome of cosmic evolution? One of the most important lessons from astrobiology comes from studying extreme life on Earth. For a long time, scientists believed life could exist only in mild environments like oceans and forests. That idea changed when microorganisms were found living in boiling hot springs, frozen Antarctic lakes, acid pools, and deep sea hydrothermal vents. NASA and other research agencies study these organisms called extremophiles because they survive under conditions that resemble environments on other worlds. These organisms do not just tolerate heat, cold, pressure, or radiation. They depend on them. This shows that life is far more adaptable than we once believed, capable of surviving in places previously thought to be uninhabitable. A second major discovery comes from exoplanets, planets orbiting stars beyond our Sun. Over the last few decades, astronomers have confirmed thousands of them using space telescopes and ground-based observatories. Many of these worlds lie within what scientists call the habitable zone of their stars, where temperatures allow liquid water to exist on the surface. Water is essential for life as we know it because it allows complex chemistry to occur. These discoveries have dramatically expanded the number of places in the universe where life might develop, turning what once seemed rare into something potentially widespread. A third breakthrough comes from our own solar system. Two icy moons, Europa orbiting Jupiter and Enceladus orbiting Saturn, contain vast oceans beneath their frozen surfaces. These oceans are kept warm by tidal heating caused by their planet's gravity. Space missions have detected water, salt, and organic molecules in plumes erupting from Enceladus, and strong evidence points to a salty ocean beneath Europa's ice. These environments may resemble the deep ocean ecosystems on Earth, where life thrives without sunlight, powered instead by chemical energy. This means that habitable environments may exist not only on planets but inside the moon as well. Together, these discoveries reshape how we think about life. They show that biology is resilient, flexible, and deeply connected to planetary and cosmic processes. The search for life beyond Earth is not only about finding aliens, it's about understanding how life emerges, survives, and evolves in a universe filled with extremes. In studying astrobiology, we are learning that life is not fragile. It's one of the most powerful and persistent forces the universe has ever produced. One of the most powerful tools ever built to study the universe is the James Webb Space Telescope. Its deep-field images represent one of the deepest looks into space and therefore into time that humanity has ever achieved. This single image contains galaxies whose light has traveled for more than 13.5 billion years before reaching us. Some of these galaxies formed only about 300 million years after the Big Bang, when the universe was still in its earliest stages. At that time, the first stars were igniting and the first galaxies were assembling from clouds of primordial gas. What we see in the deep field are not just points of light. Each tiny dot is an entire galaxy containing billions of stars, planets, and potentially countless worlds. Many of those galaxies are small and irregular because the universe was still young and its structure was still forming. Over cosmic time, gravity slowly pulled matter together, building the large spiral and elliptical galaxies we see today. The reason this image works as a time machine lies in the nature of light. Light travels at a finite speed about 300,000 kilometers per second. When we observe something that is billions of light years away, we are not seeing it as it is now. We are seeing it as it was when that light began its journey. In this sense, astronomy is the study of history written in photons. The James Webb Telescope was designed to see this ancient light. As the universe expands, light from the earliest galaxies is stretched into infrared wavelengths. Webb's instruments are optimized to detect this faint infrared glow, allowing it to peer deeper into the past than any previous telescope. These observations have already changed our understanding of how quickly galaxies formed and how early heavy elements appeared. Some galaxies in the deep field seem more massive and more structured than expected for such an early time in cosmic history. This suggests that star formation and galaxy growth may have occurred faster than many models predicted. The deep field does more than show us distant objects. It reveals the long arc of cosmic evolution, from the first stars to the complex universe we inhabit today. In every pixel, we see the results of gravity, nuclear physics, and time shaping matter over billions of years. By studying these ancient galaxies, we learn not only where the universe came from, but how the conditions that eventually led to planets, chemistry, and life were created. The James Webb Space Telescope allows us to place our own existence within a vast unfolding cosmic story. Everything we observe in the universe, from atoms to galaxies, is governed by a small set of fundamental principles. At the deepest level, reality is shaped by matter, energy, space, and time, connected through a few powerful physical laws. Four fundamental forces control how everything behaves. Gravity is the force that shapes the cosmos. It governs the motion of planets, stars, galaxies, and even the expansion of the universe. It binds matter into structures on the largest scales. Electromagnetism controls the behavior of charged particles. It powers atoms, chemistry, light, electricity, and all biological and technological processes. The strong nuclear force binds atoms and neutrons together inside atomic nuclei. Without it, atoms could not exist, and neither could stars or life. The weak nuclear force allows certain types of radioactive decay and plays a crucial role in nuclear reactions inside stars, including those that produce the elements necessary for life. Together, these four forces determine how matter forms, how energy flows, and how the universe evolves. One of the most important discoveries about the universe came from the cosmic microwave background radiation. This faint glow fills all of space and is the oldest light we can observe. It was emitted about 308,000 years after the Big Bang, when the universe cooled enough for atoms to form and light could travel freely. This radiation acts like a fossil imprint of the early universe, allowing scientists to measure its age, composition, and geometry with remarkable precision. Those measurements revealed something surprising about what the universe is made of. Only about 5% of the universe consists of ordinary matter, the atoms that form stars, planets, and everything we can see and touch. About 27% is dark matter, an invisible form of matter that does not emit or absorb light. We detect it only through its gravitational effects. Dark matter forms a kind of cosmic scaffolding, shaping how galaxies form and how light bends as it travels across space. The remaining 8% is dark energy, a mysterious form of energy that is causing the expansion of the universe to accelerate. Instead of slowing down under gravity, the universe is expanding faster over time. Dark energy is one of the greatest unsolved problems in modern physics, with no confirmed explanation yet. Together, ordinary matter, dark matter, and dark energy define the large-scale structure and fate of the cosmos. This means that most of reality is invisible to us, known only through its influence on space, time, and motion. What we can see is just a small fraction of what exists. Understanding this cosmic balance is essential for understanding how the universe formed, how it evolves, and what it may become. Reality is not just made of things, It's shaped by deep physical forces and hidden components that govern the entire fabric of existence. Astronomy is one of the oldest sciences, but it's also one of the most revolutionary. From its beginning, it has transformed how humanity understands its place in the universe. Each new tool, each new observation has pushed us beyond the limits of our previous beliefs. That transformation began in a decisive way in 1609 when Galileo Galilei pointed the telescope toward the sky. With that simple instrument, he observed mountains on the moon, countless new stars, and the moons of Jupiter. These discoveries showed that not everything in the universe revolves around Earth. They provided direct evidence that the Copernican model was correct and marked the beginning of modern science. The universe suddenly became larger, more complex, and far less centered on humanity than anyone had imagined. 3.5 centuries later, humanity took another dramatic step forward. Between 1969 and 1972, 12 astronauts walked on the surface of the moon during the Apollo missions. For the first time in history, a species left its home world and explored another. These missions were not only technical achievements, they were a demonstration that human curiosity, combined with science and engineering, can overcome what once seemed impossible. The moon became a symbol of what exploration can achieve. Today, that journey continues through NASA's Artemis program. Its goal is to return humans to the moon, this time to stay. Artemis plans include building long-term lunar infrastructure, using the moon as a laboratory for science and as a testing ground for future missions to Mars and beyond. The moon is becoming a gateway to the rest of the solar system. Across all these eras, from Galileo's telescope to modern space missions, one pattern remains constant. Every discovery opens new questions. Each answer reveals deeper mysteries about the universe, about time, about matter, and about life. On December 24, 1968, something extraordinary happened. As the Apollo 8 spacecraft orbited the moon, astronaut William Anders looked out the window and saw something no human had ever seen before: the Earth rising above the lunar horizon. In that moment, he took one of the most important photographies in human history, the image we now call Earthrise. At first glance, it looks simple, a small blue and white sphere floating in the darkness of space. But that image carried a meaning that science, politics, and culture had never fully grasped before. For the first time, humanity saw its home from the outside. Until then, Earth had always been our center. Every map, every culture, every history placed us at the heart of the existence. Earthrise changed that. It showed our planet as a tiny, fragile oasis suspended in a vast and silent universe. There were no visible borders, no nations, no divisions, just one living world. The single image transformed how humanity understood itself. It played a powerful role in inspiring the modern environmental movement because it revealed something undeniable. Everything we care about, every ecosystem, every civilization, every future exists on that small, delicate sphere. From space, Earth is not infinity. It's not invulnerable, it's precious. The photography also carries a deeper scientific and philosophical message. It shows that our planet is isolated in a cosmic sense. Life on Earth is not spread across the universe. It's concentrated here, in a thin layer of atmosphere and water wrapped around a rocky sphere. The conditions that allow oceans, air, and biology are rare and fragile. William Anders later said, "We came all this way to explore the moon, and the most important thing is that we discovered the Earth. That sentence captures the true impact of Earthrise. Space exploration did not make us feel more distant from home. It made us realize how deeply connected we are to it. This image reminds us that science does more than expand knowledge. It changes perspective. It shows us who we are, where we live, and what we must protect. From the silence of the moon, we learned how extraordinary our world truly is. Across this journey, one idea becomes clear. The universe is not something distant from us. It is the system that produced us. Astronomy shows that the atoms in our bodies were forged inside stars, the carbon in our cells, the oxygen in our lungs, the iron in our blood, all come from stellar explosions that occurred long before Earth existed. In a literal sense, we are made of cosmic history. We carry within us the memory of ancient stars. This changes how we understand connection. We are not observers standing outside the universe. We are expressions of it, shaped by the same physical laws that govern galaxies, black holes, and the expansion of space itself. When we study the immense scale of the cosmos, with its billions of galaxies separated by vast regions of emptiness, the existence of life becomes deeply meaningful. In a universe where most places are cold, dark, and lifeless, the emergence of biology, especially conscious thinking life, is extraordinary. It's not trivial, it's rare, fragile, and precious. Time also takes on a new meaning. Our lives are short when compared to billions of years of cosmic evolution, but that does not make them insignificant. It gives them context. Every human life becomes part of a long chain of events that began with the birth of the universe itself. Meaning is not reduced by scale, it's enriched by it. The universe becomes a kind of classroom, one that is always open. Through observation, measurement, and imagination, it invites us to keep learning. It challenges assumptions, expands perspective, and forces us to rethink what is possible. Through astronomy, we don't only discover distant galaxies or ancient light, we discover something about existence itself. We learn how matter becomes complex, how time flows, and how a universe governed by physical laws can produce curiosity, intelligence, and reflection. In that sense, humanity is the universe becoming aware of itself. So the invitation remains open. Keep looking up, keep wondering, keep questioning. The cosmos still has many stories to tell, and we are part of that story. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Inspired by Carl Sagan, Pale Blue Dot, 1994. Thank you so much. And please, leave your comments, and I'm looking forward to see you on the next video. Please subscribe to Free Astroscience channel.